Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last few lectures, we have been discussing the quantum mechanical solution of hydrogen atom problem. We have discussed the eigenvalues of hydrogen atom, the energy levels, the emission spectra, and we have also started discussing the eigenfunctions. In particular, we are paying close attention to the radial functions of the hydrogen atom eigenfunction. And so, in our last class, we discussed radial functions for 1s and 2s orbitals, and today we would continue our discussion and would try to find the radial solution for one wave function of a hydrogen atom where L is not 0. So, our first example that we would consider in today's class is when I want to obtain R21. So, this is 2p orbital because n is 2, the principal quantum number, and L, the azimuthal quantum number, is 1. This is the general definition of the radial wave function. You see 1 over r multiplied by rho to the power L plus 1, where rho is the dimensionless coordinate given by this relation over here, where Z is the nuclear charge. In case of hydrogen atom, it is 1. In case of other hydrogen like atoms, for example, helium plus or lithium di plus, in those cases Z will be greater than 1, divided by A is the Bohr's radius, n is again the principal quantum number multiplied by r. So, this quantity is rho. We have to do this rho to the power L plus 1. Since L is 1, therefore, we would have L plus 1 as 2. So, we would essentially write Z over A n square r square, because r to the power L plus 1 multiplied by e to the power minus rho, where rho is Z over 2 a r. Here n is n will next time when we write, we will make this n is 2, n as 2. So, this is the exponential function, one of the two asymptotic solutions. This one was one asymptotic solution, this is the other asymptotic solution. And now, we would look at the main body solution of the eigenfunction, which is given by the power series expansion. So, when you see here, j goes from 0 to n minus L minus 1. Since n is 2, L is 1, 2 minus 1 is 0. So, therefore, I am left with only one term in this series expansion, and that term is B 0, which is a constant. So, I still do not know this constant. So, I bring this to the left hand side, and I see 1 over r multiplied by r square. So, that will give me r multiplied by. So, this is the radial function corresponding to 2p orbital. What do I see? I see a B 0, the unknown. I already know how would I get this unknown. I would simply normalize this function. When I normalize this function and make it 1, I would determine the value of B 0. I would encourage you to do this for yourself. Multiplied this, so this constant is obtained from by normalization, multiplied by this term where Z is the nuclear charge and A is Bohr's radius. So, therefore, this is also a constant. So, these two terms are constants, and now we have the functional dependence of this radial function is given by this equation over here. This shows that the radial function is r multiplied by an exponentially decaying function. So, now we have, if we want to plot R21 as a function of r. So, r can go from 0 to infinite. You can see that this function would never become negative, because we have r and which should be a positive term, and then this is an exponentially decaying function. When r goes to 0, unlike the s orbitals, whether 1s or 2s, unlike s orbitals, since when r goes to 0, this function will become 0, because I have this term. For lower value of r term will dominate. So, we would see an r type of rise, but as we go higher and higher value of r, then we see that there is this exponentially decaying function which will overcome, and then at the end we would get something like this. There will be a long tail which would reflect the decaying function of e to the power minus z by over 2a. And one more thing to note is that we do not have any nodal structure in this case, because this 0 that comes is the asymptotic solution, and this 0 which comes as very large value of r, also an asymptotic solution. For the intermediate value of r, we do not see any node. So, therefore, 2p orbital we see that there are no radial nodes. Just to remind you, 1s orbital also did not have a radial node, whereas 2s orbital had a radial node. So, in this way, using this general expression, we can write down the radial part of the hydrogen atom's eigenfunction for any value of n, for any value of L. We would now look at some general features of this wave function that is given by this radial wave function that is given by this relation. One thing that you would notice here, we have these two terms rho to the power L plus 1. So, rho has a direct dependence on r multiplied by the constants. We will, for the moment, we will not be worried about the constants, and we will look at the functional forms of these radial wave functions. We have 1 over r multiplied by rho to the power L plus 1, where rho is this constant multiplied by r. So, in essence, I have r to the power L plus 1 divided by r. So, therefore, this I will get from this term, I will get a r to the power L kind of term, where L is the orbital angular momentum of the electron, multiplied by e to the power minus rho, which is again e to the power minus some constant multiplied by r, but mind you, this constant depends actually on the value of n. So, I have one r to the power L term, another exponentially decaying function, and then I have this polynomial, the power from the power series expansion. Let us first look at r to the power L. When L is 0, I have this term becoming 1 for L equals 0. For all other values of L, when L is 1 or 2 or 3, I have r square or r cube kind of term. So, when r to the power 0 is there, when the term is r to the power 0 or a constant, when the value of r becomes 0, this function does not become, radial function does not become 0. When does that happen? That happens when L equals 0, that means all s type of orbitals. So, we have seen that for s type of orbital 1s, 2s, 3s and so on and so forth, the radial part of the wave function does not vanish at r equals 0. On the other hand, when we have L equals 1 or 2, we will have r dependence or r square dependence or r cube dependence at low value of r. So, this is for the lower value of r. As soon as r, the distance between the electron and nucleus increases, the second term, the exponentially decaying term dominates. So, this is the asymptotic solution for the long range of r, that means large value of r. In that case, you would see that this function will be a decaying function. As I increase my n, when n is large, that means instead of, I am talking about now 1s, 2s, 3s, 4s, where n is increasing, or 2p, 3p, 4p, where n is increasing. So, when I increase my n, I see n becomes larger. So, therefore, this function becomes smaller, and therefore, what I would experience is a slow decay of this function. This exponentially decaying function will have a slower decay for larger value of n. What does that mean? That means, when n is large, my wave function, the radial part of the wave function will survive even for larger value of r. That means, higher principal quantum number would allow the electrons to stay farther away from the nucleus. Small r is the distance between the electron and the nucleus. So, these are the two asymptotic solution. Now, the main body solution of this problem is given by this power series. You would see that depending on the value of n and L, I have this polynomial which would come out. So, what will be the order of this polynomial? The order of this polynomial is going to be n minus L minus 1. So, you would have seen this when 1s orbital, it was 1 minus 0 minus 1. So, it was 0th order, that means it was a constant. When it was 2s, it was 2 minus 0 minus 1. So, it was b 0 plus b 1 rho. So, it was a first order term, we had a first order term, and so on. When you go for higher values of n, you would see higher order polynomials coming out. But I have the order of polynomial here as n minus L minus 1, and then when I solve these polynomials, I would find actually n minus L minus 1 number of roots for this. That means, at n minus L minus 1 number of times or number of places, this function will become 0, this polynomial will become 0, and when this polynomial becomes 0, the radial part of the wave function will also become 0, and then I will get a node, and these nodes will be called radial nodes. So, we see that from this series expansion, I am expecting n minus L minus 1 number of radial nodes in my orbitals. This will discuss here. What we show is the functional form of hydrogen atoms radial functions. So, this we have already seen R10, which is some constant multiplied by an exponentially decaying function, where this decay is over minus z r by a. Look at 2s, I have a polynomial of first order, and at how many places this function will become 0? Of course, you know that this will become 0 at one value of r, and that is the value of and when we look at 3s. So, in this discussion, let us focus on 1s, 2s and 3s. So, when I compare 2s and 3s, I see that 3s orbital has a polynomial of second order, and then you would see that at two different values of r, this function will be polynomial will become 0, and therefore, R30 will have two radial nodes. This is what is depicted here in this diagram, taken from the molecular quantum mechanics book by Atkins. You see, for 1s orbital, the function is an exponentially decaying function. For 2s, you see, in our previous lecture, we discussed at this value of rho, we experience a node, and after that, when r is actually greater than 2a over z, in that situation, we have the function becoming negative, and then after when we go to larger value of rho's, the exponential function will dominate, and then this function approaches to 0 asymptotically. So, this is 2s orbital, its radial function, and we see one node, and here I have 0 nodes. In case of 3s, I see that there are two different places where I experience the wave function will become 0, and how would I get that? It is simple. I just have to take this polynomial and find the roots of this, and I would see that there are two values of r where this will become 0. So, therefore, 3s has again two number of radial nodes. Why do we saw that the number of radial nodes turned out to be n minus L minus 1, and in case of 1s, it is 1 minus 0 minus 1, it is 1. In case of 2s, for 1s it is 0, for 2s this value is 1, and for 3s it is 2. So, we see that the functional forms that we get have some physical justification, and using them we can derive the location of the radial nodes for different functions. We would now look at, instead of looking, so far we discussed the S type of orbitals. Please note that in all the S orbitals at r equals 0, the radial function is not 0, rather it has got some finite value, because when r becomes 0, we would have some constant that would come up here. Now, we will look at some other functions. Here I am showing the radial functions for 2p orbital, 3p orbital and 3d orbital. Let us first look at 2p. 2p is given as this function. We have just derived the functional form of this, leaving aside the constants. We see that we have this r multiplied by the exponentially decaying function. So, you can see at lower value of r, this r term dominates the so at r equals 0. So, therefore, the function becomes 0, and after some time when r becomes moderately large, the exponential function dominates, and we see that the function is pulled down and brought asymptotically to the value of 0. So, the radial part of the function again becomes 0 at very large value of rho. Unlike s orbital, the p orbital's radial function becomes 0 at r equals 0. But here again we notice that there are no nodes. The value of 0 that we see are asymptotic solutions where they become 0, but in the intermediate region we see no radial nodes. So, there are no radial nodes here. Now, let us look at 3p orbital, which is here 3, n is 3, l is 1, and now again I see here this function. This is, I have a polynomial multiplied by an exponentially decaying function. When you look at these two terms, so you have some constant multiplied by r and r square. So, I can take r common out of this. So, I have simply z by a minus z square by 6 a square r. So, it is essentially when r goes to 0, this function becomes 0, 3p function 0, and how many radial nodes can I expect? Since I have a polynomial of the first order. So, I will have one node. So, this is the node in the 3p. How can I find the value of this node? I would make, when I make this find the root of this polynomial over here, I will see that the value of r, I can find out the value of r where this function is 0, this polynomial is 0, and therefore, that would be the place where this radial function will develop a node. And we will see that at moderate value of r, the radial function becomes negative, and then at larger value of r, the exponential function dominates, and then the radial part of the function approaches to 0 asymptotically. So, again we see that number of nodes that we see should be n minus l minus 1. So, we have looked at 3p, which should have one node, and now let us look at 3d. So, where l is 2. When L is 2, you see the functional form is, apart from the constants, the functional form is r square. We discussed that since it has L value of 2, it should have r to the power L type of term, that is true, and multiplied by an exponentially decaying function. So, where the decaying function is, the function decays slowly, because it is minus z r divided by 3a because of this 3. So, now let us look at small value of r. At r equals 0, this function becomes 0 because of r square term, and we should not find any node from this function. That is true in case of 3D. As you see, for small value of r, in case of 2p and 3p, we saw this function increasing as r term, but here we see the function increasing as r square, and eventually the exponentially decaying function dominates, and it pulls down to the radial part of the wave function to become 0 at asymptotic limit. And in this case, again we have 0 node, because we see 3D 3 minus 2 minus 1. For d orbital L is 2. So, this becomes 0. So, therefore, I have 0 node here, 0 node here, and 1 node. Mind you, all these nodes are the radial nodes. So, we looked at the forms of these radial functions. Now, what we would do is that we would, if you remember, we took the total wave function and expressed it as product of two functions, one radial, another angular function, and we said that the angular function is the spherical harmonics, which are the eigen functions of the angular momentum operator, and the radial part of the solution is something that we had been discussing. The angular part of the solution we have already discussed in great details when we were discussing angular momentum operator and its eigen functions. We have now we will combine the two, the radial solution and the angular solution, and we will first discuss this for s orbital. Here I am showing the radial solution of one s orbital, and the angular part of the solution is when this is since my psi n l m would be r n l y l m. So, for these three quantum numbers n l m, I have my radial function depends on n and l, and angular functions depend on l and m. L connects the radial and the angular part, this L quantum number. So, since I have one s orbital, or for that matter I can write r 2 0, I have r 1 0 y 0 0, r 2 0 y 0 0, r 3 0 y 0 0. So, this is 1 s, this is 2 s, this is 3 s, because for s orbitals L value is 0, and when L is 0, m is only one possible value for m, and that is also 0. So, now if I know the radial functions, I simply multiply the angular functions, the spherical harmonics, and then I find the final function of the final form of the eigenfunction of hydrogen atom. Now, let us look at the s type of orbital. The angular component of the s orbital is actually independent of any theta or phi. If you recall, we discussed that this function y 0 0 is constant throughout the theta and phi space. So, in the spherical coordinate system, we had this is 0. Suppose we defined our x, y, z like this, and the angle that it made with z axis is theta, and the angle that it made with the projection of this point to the xy plane is phi. Phi goes from 0 to 2 pi, and theta goes from 0 to pi, and this value is r. So, the radial function defines the r dependence, the distance between the dependence on the distance between electron and nucleus. No matter what value of r we are, suppose we fixed one value of r, that means this is my nucleus and this is where electron, I can choose the value of r, and the dependence of this r is already defined in this radial function. I can choose a particular value of r and then decide to go around the theta space, that is from 0 to pi, and go around the phi space, that is 0 to 2 pi for this 1 s orbital or 2 s orbital, and so on and so forth. When I do that, since the angular part of the solution is constant throughout theta and phi space, so therefore, what I am going to get is that I will have a constant distribution of the total wave function all over theta and phi space, and when I translate that to a geometric space, you would see that I will have a sphere. This sphere is coming because I have equal distribution or constant distribution of the s orbitals angular wave function, but remember this radial function has r dependence, whereas theta and phi are constant throughout. So, therefore, we will get a spherical shape for the s orbitals, whether it is 1 s, 2 s, 3 s, does not matter, as long as it is an s, it will have spherical shape. But what happens, how do we distinguish 1 s and 2 s, we will discuss that in a moment's time, but for any s type of orbital, the shape of the function is spherical. Now, what we do is that we would further move to the case of p orbital. Again the same analogy, I have the system defined as r, this is my z axis, this is x axis, this is y axis. So, this angle is theta, and the angle that it makes to the projection of this point on xy plane is phi. So, I am now showing the 2p radial function over here. This is what we had discussed, and this is its functional form. So, I know how this radial function will change as I increase r, from r equals 0, which is over here, that means the nucleus is here and the electron is moving radially. So, a different value of r, how this radial function changes, I know that here I show. Now, what I am showing here are the 3 angular function corresponding to L equals 1. So, you remember when L equals 1, I have 3 different values of m, that is 0, plus 1 and minus 1. So, these are the 3 functions y 1 1, y 1 0 and y minus 1. One thing that you would notice is that these functions are in the complex form. So, in particular in case of phi coordinate, they are written in complex. I can, instead of writing y 1 minus 1 or this instead of writing them in the complex form, I can convert them to the so called real form. So, here I am defining p x, p y, p z, which is we are very familiar with it, as a linear combination of p minus p plus and p that gives me p x and p y, and p z is equivalent to p 0. When I do this transformation, that means I come from complex function to the set of real function, I then see a sin theta cos phi or sin theta sin phi term for p x p y, and I have a cosine theta for p z term. So, you see when phi value is pi by 2, then this cosine phi becomes 0. When does phi becomes pi by 2? When phi is the angle of this projection of this point onto xy plane from x axis. So, phi will be pi by 2 when the point exists anywhere on the z y plane. So, I would see that when phi equals pi by 2, that means the point is on y z plane, I would see the wave function, the angular part of the wave function becoming 0. So, therefore, I develop an angular node. Similarly, in this case for p y, when phi is 0, that means when it is on x z plane, I develop an angular node. And this angular node, if I define a plane, so on this plane the wave function vanishes, but the wave function exists above the plane and below the plane. So, what we are drawing is the famous dumbbell shape of the p type of orbitals, and similarly for cosine theta, this term will become 0 when theta equals pi by 2, and theta is pi by 2 when we have the point on xy plane. So, therefore, this also develops another angular coordinate. So, since we have an angular node in xy plane, we call this orbital pz. When the angular plane is on xz plane, we call this orbital py, and when the angular plane is on yz, we call this orbital px. So, in today's lecture, we discussed the radial nodes and the angular nodes of hydrogen atoms eigenfunctions. We will continue our discussion in the next class. Thank you for your attention.